what we did last time, we learned how to locate the satellite in a rotating coordinate system, the one that is fixed to the Earth, with z-axis going through the North Pole, x-axis going through the 0 latitude, 0 longitude, and y-axis pointing to east, right? So that was the system that rotated around the Earth. And what we need to cover today is the case where you're now at the surface of the Earth, satellite is flying around the globe, and the question is, how do I determine the direction where I need to point the antenna so that I catch that satellite, right? So if you think about Earth being locally flat, right? You are on a sphere, but locally you're flat. So what you need to understand is which direction I need to look. That's your azimuth angle. And then how high up in the sky do I need to look, which is your elevation. So what we're going to do today is we're going to assume that we know XR, YR, and ZR. And we're going to walk through the process how you determine azimuth and elevation from any point on the globe so that you can point your antenna towards that satellite. In cases of geostationary satellites, this is a one-time effort, right? Because they are geostationary, so they are kind of moving along with you. And the problem simplifies tremendously. But in case of satellites that are orbiting the Earth, like LEO or MEO satellites, and traveling across the sky, then this becomes a tracking problem. What we're going to cover today works for both cases. As a matter of fact, if it works for the second case where you can generally track the satellite, then it works when the satellite is sitting still relative to you. Right? So the process of pointing antenna is kind of a two-step process. In the first step, I have to explain something that's called SubSatellite Point and how you actually determine the location of the SubSatellite Point, because our calculations of the azimuth and elevation are going to be done relative to that SubSatellite Point. So let's first explain what the SubSatellite Point is. SubSatellite Point is an easy concept, right? You have a satellite that is here in the system XR, YR, ZR, rotating around the Earth. SubSatellite Point, to obtain the SubSatellite Point, you take the position of the satellite, connect with the center of the Earth. At some point, this line is going to go through the surface of the Earth, and that's going to be your SubSatellite Point. It's a projection of the satellite point on the surface of the Earth, and that is on the line that connects satellite to center of the Earth. Right? So if you know these coordinates, XR, YR, and ZR, then what you need to do is you need to determine the latitude and the longitude of the SubSatellite point on the surface of the globe. Now, it might be a general knowledge, but let me spend a couple of minutes talking about it. I don't know, can I turn on these lights? Maybe not. Let me stop here. And spend a couple of minutes just explaining to you what most of us know, but it's never good practice to take anything for granted, right? So, what's the coordinate system that is the most common when it comes to locating things on Earth? It's our latitude-longitude system. It's you assume the position is on the sphere, and to locate the position on the sphere, you need two angles, right? You need to somehow specify two angles. The most common way of doing that is we specify latitude and longitude. To do that, here's our globe. This line that I drew here is equator, right? So that's one circle that we're going to take as a reference circle. The other circle goes, from north to south, and then back the other way. Right? We define two angles. This angle is called latitude, right? And it tells you how far you are from the equator in angular units. This is the center of the world, right? Center of the Earth. What is the largest latitude? Plus 90 degrees, right? Where are you when you're plus 90 degrees? You're on the North Pole. What's the smallest latitude? Minus 90 degrees. And that's where when you're at minus 90 degrees, you're at the South Pole. So every other latitude is in between it's in between plus 90 and minus 90, right? If you're on equator, you're at a latitude of 0 degrees. Now, this circle here is your longitude circle, and we have adopted that the circle that goes through what is called Greenwich, which is just outside of London, we call that circle as a 0 longitude, right? And so this angle here is going to be longitude, right? And unlike, so then we have to define which direction we take plus and which direction we take minus. For most, I guess, in most cases, we define that going east is plus and going west is minus, right? So the longitude can go from 0 to plus 180 degrees or from 0 to minus 180 degrees, right? So when we define it this way, then we unwrap the world into a rectangular map. That's the map that you kind of see all the time. This is equator, right? So this is 0 degrees of latitude. This is Greenwich. This is 0 degrees longitude. And this is plus longitude. And this is plus latitude. And this is plus 90 degrees latitude, minus 90 degrees latitude. This is 0. This is plus 180. And this is minus 180. Right? So that's how we consider the map. This thing here happens to be right outside of east coast of Africa. Here in Melbourne, we're somewhere here. We're on I believe 80 degrees away from the Greenwich on the 80 degrees longitude and about 28 degrees latitude. So that's where we are located. Okay, the way how a lot of times, when I came out of school, it's always I had to always stop and think which one is the longitude and which one is the latitude, right? They should have named them at least with a different first letter. And then when I started working, there was a technician, and he says, "You know how I remember?" And I said, "How?" He says, "Longitude circles are always long," right? So and that's how I remember it today. If you move latitude right-wise, you can see that the circles are becoming progressively smaller, right? So latitude direction, as you move up, these circles are becoming smaller and smaller, right? But if you move around the longitude, the circles are always the same length. So they're long. So longitude is long, right? Latitude is not, right? It's not something that is scientific or anything, but it's a good way to remember things. And it worked for me, so I'm kind of sharing it with you. All right, so what is it that we need to do? If I have XR, YR, and ZR, how do I get longitude and latitude of the subsatellite point, right? How do I get these coordinates? And this should be coming up, right? This is coming up here. So these are the calculations, right? You have this one here that says this is the latitude, right? The latitude in your book uses capital letter and longitude uses a lowercase letter. So latitude of your subsatellite point is given as pi over 2, or 90 degrees, minus inverse cosine of ZR over the radius, right? So that's the location of the latitude. And then longitude, we define 4 quadrants, right? 4 quadrants and depending on which quadrant you are in, this is how you would calculate the longitude. If you look from the North Pole, these quadrants are going, I guess, counterclockwise. So this first quadrant is Eastern Europe, then it comes Asia, then it comes Asia Pacific, and then this is Atlantic, right? So we're here in a 4th quadrant, right? Our XR is greater than 0, so that means we are on I guess this side of the globe, because your XR is going this direction, so we're here, right? And our YR is negative, so that we are west of this zero latitude plane, right? So if I give you ZR, XR, and YR, these are the 2 sets of equations that will allow you to calculate the exact position of the subsatellite point. Now, I've mentioned that several times, there are, and you can probably sense it, that a lot of these calculations, are tricky geometrically, right? And you have to be very careful. What I wanted to illustrate with these slides is, depending on how your actual orbit is, the subsatellite points may travel very interesting curves on the surface of the globe. What you need to take into account are essentially 2 things. First, the satellite is moving around the globe, but the globe is traveling itself, right? So combination of the 2 is not always easy to understand. And as I said, there are specific software packages that are designed to do these calculations. What they have is engine, which is called propagator. And the propagator, good propagators don't do only simplistic calculations that we do here that assume spherical Earth and all of these idealistic assumptions. They take into account all the imperfections. And these are some illustrations here. The one below is the subsatellite point as it travels, subsatellite point of the International Space Station. If you remember last time, the International Space Station has an orbit that's inclined about 50 degrees relative to the equatorial plane. Remember that I that we got from the 2-line element data was inclination of the orbit was 50 degrees. So if you look at this intersection with the equator, the orbit is inclined 50 degrees. And then as it travels this way, then this is how it maps. By the time it comes around, it's not going to cross at the same point. Why? Because it takes about 90 minutes for the International Space Station to come around the globe. And even though spatially it is, let's say, if the Earth were not to rotate around the sun, right? But if the Earth were not to rotate around its axis, it would cross the same point. But because now Earth rotates, it is always moving to the west, right? Because by the time it comes to the same point, Earth has already rotated. And if you look at over a period of 24 hours, then it will come somewhere close, right? Because the Earth, this point of intersection moves, as the Earth rotates. So that's how essentially the circular orbit would translate on the surface of the globe. And circular orbits that are circular inclined orbits result in these almost sinusoidal patterns on the surface of the globe. Now what you have here is a different kind, and I didn't talk too much about it, but if your objective is to cover a certain part of the globe, right? Let's say you want to cover only the United States. One of the common approaches is to make your orbit inclined and then make it very much eccentric, right? And what you do is you make it so that your apogee is on the opposite, or your perigee is on the opposite side. So it kind of zooms through through the south side of the globe, and then it's kind of your perigee is about the area that you want to cover. So it dwells around this area quite a bit, right?
Yeah.
And then it kind of goes and it zooms around and it comes back, right? Kind of goes like this, right? And what you have here is the Sirius radio. That's the radio service that we have. And it kind of gives you the pattern of how this, that radio is the path of that radio. It's a little bit misleading, and if we have time, sometimes I'll run this simulation, so you will see that, you know, it is running much faster here, and it kind of dwells about the North American continent for a long time. But you have to have multiple satellites. I think there are 3 satellites that are deployed there, and that, you know, when one is in the south hemisphere, the other 2 are about servicing the area. So you always have, you know, 3 satellites, right? There used to be two services. It used to be Sirius and XM, and one of them has 3 satellites and one of them has 2. But now they're one company, so I don't know which one is which. Right, so bottom line here is that, you know, you have to be really experienced to be able to rely on your intuition. For us who deal with this on a per lead basis, we use these tools to predict the position of the exact position of the subsatellite. Okay. So now, let's go to the second task. Now that you know where your subsatellite point is, and remember, we go through multiple steps. We first locate the satellite in the orbit. Then we, based on the orbital elements, we can locate the satellite in our fixed coordinate system, and then we use transformation to put it in a rotating system, and then we use these equations to determine where subsatellite point is. Now, we assume that we know subsatellite point, and we're somewhere on the Earth where there's antenna that we're trying to use to communicate with the satellite. And what we need to do is to determine where to point the antenna. And that involves 2 angles again. We need to know which direction, and that means azimuth in 360 degrees. And then once you determine the direction, what elevation you need to point to reach that particular satellite. So again, azimuth is 0 to 360. 0 is referencing north. When we say azimuth direction is 0, that means you're pointing straight to the north, right? And elevation goes from 0 to 90 degrees. 0 is pointing at the horizon, and 90 degrees pointing straight above, which is called zenith. Oh, one thing that is really a little bit messed up here. Unlike all the other angles, azimuth is calculated clockwise, right? So if I say azimuth is 0 degrees, that means pointing north. But if I say 90 degrees, where am I pointing? East, right? And that means your angle is calculated this way, right? As opposed to counterclockwise, where for almost every other angle, you calculate angles counterclockwise.
Even antennas, don't we do clockwise?
Which one?
Antenna.
Antennas in cellular network, because we also talk about azimuth. Azimuth in general is the angle that we align with north, and then you know, have a plus in a clockwise direction. It would be interesting to look up the history of that. That has something to do with military and watches. All right, so let's summarize where we are. We know where the subsatellite point is, and we know where we are geographically. We know the latitude and longitude of the Earth station. We know the latitude and the longitude of the subsatellite point. And the third thing that we know is the radius to the satellite, how far the satellite is from the center of the Earth. First thing that I'm going to cover here is how do you calculate your elevation angle. And the elevation angle, there are two steps here. So input data, location, latitude and longitude of the Earth station, latitude and longitude of the satellite point, and IS is the distance to the satellite. So to calculate the elevation, you go through two steps. One is you cosine this intermediate angle gamma, and you can see the calculations here. Cosine of the latitude of the Earth, cosine of the latitude of the satellite, cosine of the difference, sine of these two latitudes. You get your gamma, and then once you know the gamma, cosine of the elevation is sine of that gamma divided by what I have downstairs, and then you calculate the elevation is inverse cosine of this particular angle. Elevation inverse cosine might give you two angles, plus minus something. You always take plus because negative elevation makes no sense because it's below the horizon. Right? You cannot communicate below the horizon. So here's an example here. I'm looking at Earth station that is at latitude of plus 28 degrees, longitude at 80 degrees west. So there is a typo here on the slide. What should be the longitude? It should be minus, right? Because why? Oh, okay. Wow, getting complicated more every day. So we, as I said here, in most cases, longitude is positive if you go to the east and negative if you go to the west. So here, 80 degrees west means minus this many radians in longitude. Latitude is this, and then this is how many radians also west, right? So the Earth station is in Melbourne. These are the geographical coordinates of FIT. And this is the SubSatellite point of this particular satellite. This is the radius to the satellite. So the satellite is 38,000 kilometers, essentially in a geostationary orbit, plus minus. So I'm rounding the number. And in step one, you calculate the cosine of this angle using this formula. You get your gamma, and then you get cosine of the elevation to be this, and then you calculate the elevation to be 10 degrees. So that's how you would calculate just following these two equations. The RE here is the radius of the Earth, around 6,370 kilometers. So just this, I suggest when you go through these notes, go through these, use these as intermediate results that you would obtain by doing these kind of calculations. Now, unlike calculation of the elevation, calculation of the azimuth is not straightforward. There are quite a few cases. There are actually 8 cases to consider, and 8 scenarios that might happen depending whether you are on the north hemisphere, whether you are on the southern hemisphere, and the relationship between Earth station and SubSatellite Point, which one is more west of the other one. So again, here the input data are latitude and longitude of the Earth station, latitude and longitude of the SubSatellite Point, and then the distance to the satellite. Now, the presented algorithm, as it says here, works for a general case, right? These equations simplify quite a bit when you're talking about geostationary satellites, but let's present the general case. Let's first look at northern hemisphere. we have 4 cases for the northern hemisphere. We actually distinguish these 2 scenarios with, we look at 2 points, A and B, and each one of them can be either Earth station or subsatellite point. So this is 2 cases, right? One case is A is A is west than B, and then A is where the subsatellite point is, B is where the Earth station is. So that's the first case. A west than B, but A is Earth station, B is subsatellite point. A is east of B, A is Earth station, subsatellite point, and A is east of B. This is subsatellite point, Earth station, right? So you have 4 different cases. I guess they're given here, right? And these are the calculations. First, you would use the latitudes of A and B and calculate tangent of 1/2 y minus x, 1/2 y plus x. You know, you take inverse tangent here, so you get y minus x, y plus x, and then based on you get 2 equations with 2 unknowns. You can solve for y and x, right? And once you know y and x, then you match your scenario to one of these cases. So if you're, let's say, case 1, that means subsatellite point is in a case 1, A is west of B, so this is the scenario. And the case 1 says subsatellite point here is, and the Earth station is at the point B. And then you would calculate x and y, and then whatever you get from y, you take 360 degrees minus y, and this is the azimuth that you need to point. And then you have all the other 4 cases, that all the other cases that you need to, you can incorporate. So really here you have to be careful to match appropriate case to the scenario that you're trying to do the calculations for. So this is for the northern hemisphere. This is for the southern hemisphere. Pretty much the same kind of calculations, just a little bit difference here in the sines and cosines and these absolute values. But you calculate C first, you plug C into these equations, you calculate this and this, you take inverse tangent, you get y minus x and y plus x, you sum, you get y, you take the difference, this minus this, you get x, right? Once you know x and y, then you can match your particular scenario to one of these cases, and then you have 4 cases here as well, and then depending on which case you end up with, you would calculate azimuth based on this last equation. Now the question is, what happens is one of the points is on northern hemisphere and the other one is on the southern hemisphere. In that case, you use the equations for the northern hemisphere. So the northern hemisphere equations are good if at least one of the points is on the northern hemisphere, either subsatellite point or the Earth station. Right? Now you see there's a lot of these equations, and what needs to be done is the easiest way to do that is to sit down, dedicate some time, and then make a spreadsheet that will do all these calculations for you. And if you look at what I have provided on my website, is going to be this Excel spreadsheet. And let me explain to you how this Excel spreadsheet works. This is the one that does all the calculations that are given in on these formulas on the slides. And my advice and my hope is that you're going to go through this Excel spreadsheet and verify all the calculations that are behind these fields. But how does this Excel spreadsheet work? Well, here's where you specify the locations of your Earth station. So let's say, let's just do, I think I have an example here on the slide. So let's just work through that example using this Excel spreadsheet. So what does the example say here? It says, calculate, this one, next one. It says here, calculate azimuth for the following data. So the latitude is 28, 0.06, and longitude is 80 degrees. So you're essentially here in Melbourne, and we're trying to determine azimuth and elevation to the satellite that's with the subsatellite point given here. So let me punch in the data. I don't know if you can see. So here, I'm going to enter the latitude. The latitude is 28 degrees north, so that's positive. So that's 28.06280. And then it says enter the longitude. The longitude is 80 degrees west. So this is going to be minus 80.62311. So that's where the Earth station is. The radius of the Earth is 6,378 kilometers. Then we look at the subsatellite point here. Subsatellite point has a latitude of 49 degrees north. So let's punch that in. 49, 5432. North, it's positive. Then it says it has a longitude of 48.2967 west. So that means negative. So it's minus 48.2967. Negative. And then radius to the satellite is 6,738. So it's a very low orbiting satellite, 6,738. Only 300-400 kilometers above the surface of the Earth. This is, I assume, International Space Station again. Now, let's, before we look at the result here, kind of ballpark it. Let's see if you guys can at least speculate where azimuth and the elevation for this satellite are going to be. Let's see first, go to our map here. We are at 20 degrees north, so we are somewhere here, plus 20, what is it exactly? 28 degrees north, right? And then we are 80 degrees west. So this is location of the Earth station, right? The satellite itself is 49 degrees north, so it's somewhere here, 49 degrees north. And it is 48 degrees west, so it's somewhere about here, right? So what should be our azimuth? Somewhere around 40-something degrees, right? If it will do the precise calculation using the spreadsheet, but it cannot be 135 degrees, right? You can see from this map. Now, this is a low orbiting satellite. So, what do you expect your azimuth, your elevation to be? Very close to horizon, right? Because except when it's really at the same latitude and longitude where you are, this satellite is almost all the time on the horizon, right? Because it's flying really low in the sky. So what does it end up being here? I give you all the intermediate calculations here, but you see, okay, azimuth ended up being 40 degrees, and does it give me an elevation here anywhere? No. So let's go to the spreadsheet here. So now the spreadsheet gives you calculations for all 8 cases, right? Here I have entered the location of the Earth station. I have entered the location of the subsatellite point, and then I guess elevation calculation is only one, right? Because that does not depend whether you are on a northern or southern hemisphere. We have the formula. So you calculate this angle gamma first, that intermediate angle, so I get the cosine. I calculate the gamma, and then cosine of the elevation is that long equation with the sine of gamma, and then you calculate elevation, and here it gives me that if I want that the elevation to the satellite is around 10 degrees, so very close to the horizon, which is intuitively kind of what I expected, right? Because it's a low flying satellite. Now, if you look at the, now azimuth calculations, we have to identify which case are we working with. We're looking at the case where this is going to be A point, this is going to be B point. We are on the northern hemisphere. A is west of B, and A is where your Earth station is, and B is where the subsatellite point is. So I don't know if I spelled that. Okay, they're given to them. So I would use this section here, which is the section that pertains for the northern hemisphere calculations. Let's identify the case here. Your Earth station is in a point A, right? Your subsatellite point is in a point B. B is the point with a higher latitude. And then A is west of B. So that's our case 2. So what I need to use is, I need to use angle X, right? And if you look at X here, this is X, and then that means your azimuth is at 40 degrees, right? So if I were to point the antenna to the satellite, I would point it at 40 degrees from the north, and I would point it 10 degrees up in the air, and I would point the antenna towards the satellite, right? Okay? Any questions here? So how do you work here? You would populate the black fields. You know, all the black fields up there need to be populated. Those are your inputs. Make sure that the proper case is identified, that you understand which case are you calculating. And that case, there are 8 possible cases. You eliminate 4 right away, depending on whether you're calculating for northern or the southern hemisphere. Once you know the hemisphere, then you have to determine which out of these 4 cases you are working with. And then these cases differ by the points where your Earth station and your subsatellite point is. And then you have also which one is west of the other, right? So you have to match that based on these calculations here. And then this will determine which out of these 4 angles that are being calculated here is essentially your azimuth. Go ahead.
What do you use in the boundary conditions? Say you're right on the equator. North or south hemisphere?
No, the equations give you the same thing. But as long as one of the points is on the north hemisphere, you use the northern hemisphere equations, right? If both of them happen to be on equator, test it. I don't know. I mean, it's a normal case. Usually, you know, I've tested this spreadsheet when your satellite is on the equator. Subsatellite point for all the geostationary satellite is on the equator, right? And so this works for that case. Very few times your Earth station is on the equator as well, right? But please test it. You know, I haven't tested it for that case. Okay. Now, as I said earlier, the situation simplifies quite a bit when you're, I'm just going to not say when, simplifies for the situation when you're when your satellite is geostationary, because I think those equations are given also in the book. And that's also quite common case, because a lot of times our satellites, especially our broadcast satellites and our communication satellites, are indeed on the equator. They have 0 latitude. And you're going to find, and it's a common case that you need to point your satellite dish towards one of those locations. And you can find a lot of programs online that are kind of like applets that allow you to determine which way your dish needs to be pointed. And this is one of them. It's I think I give the URL here, so you can go there, and then what you do is you type in your location, and you pick which satellite do you want to point at, and it will actually give you your azimuth and elevation that you need to point out. So for example, here, I'm right on a, where am I? In my office here at FIT, and notice, I think this map was before we put that Harris building. So that building is missing. I'm trying to point to Galaxy 9, which is one of the satellites used for television broadcasting. And it tells me that I need to point 180 degrees, and that I need to, which is due south, right? Where is the north here? The north is this way, right? That's, this is Babcock, right? So north of Babcock. So I'm pointing 180 degrees due south, and I have to point at the elevation angle of 57 degrees. And now, okay, another thing to mention here, you know that the rotation, where the rotational axis and the north pole, the magnetic north pole, are not at the same spot, right? So a lot of these programs say, well, if you're using a compass to locate the north, then this is not really where the z-axis is. So you have to kind of compensate for north pole not being where the z-axis is, and it gives you here, if you use compass, then you point at 187 degrees, not at 180.8 degrees. There's some offset because the magnetic north pole is not the same as the rotational north pole. Right. So I guess, you know, you can compare, use this, I guess, to cross-check the spreadsheet as well. Okay. So I guess that's the last thing here. Let me kind of summarize at this point where we are. We started from the very beginning from essentially Newton's gravitational law and Kepler's equations. And then we said, well, we have satellites orbiting the Earth. How do we actually locate these satellites? And from our standpoint, we need to locate them to communicate with them. So if you're standing on the surface of the Earth, what you really want to know is how do you get, which way do you point your antenna? And we said in order to determine that, we have to kind of walk through several steps. First step was locating the satellite within its orbit. And we do that by looking at eccentricity of the orbit, looking when does the satellite go through the given point, which we usually use perigee as the point, and then knowing the one of the dimensions of this orbit, either its semi-major axis or the period, which we can relate to the size of the orbit, because we know that by Kepler's law, the period is directly related to the size of the orbit. So once we know where the satellite is in orbit, then you realize that the position of that orbit matters, right? So what we need to do is now we have to say, okay, how is this orbit positioned relative to the globe? And then we have the two-line element data that tells us inclination of the orbit, the right ascension angle, and angle of the perigee. So that helps us rotate, determine the position of the satellite in a fixed coordinate system that goes through the rotation axis of the satellite, of the Earth, and has X and Y axes that are fixed based on the distant stars. Then we go from that coordinate system to a rotating coordinate system, and then from the rotating coordinate system we determine subsatellite point. So at that point we have actually the footprint of the satellite on the surface of the Earth. Those are those subsatellite points that travel on the surface of the globe. Once we know the subsatellite point, we are in our earthly coordinate system. This is our latitude and longitude coordinate system. And now the task becomes, if I know my position on the ground, latitude and longitude, my location, and I know the latitude, longitude of the subsatellite point, and I know the radius to the satellite, which way I point the antenna. And these are the two angles that we need. One is the azimuth, which is the angle from due north in a clockwise direction, and the other one is elevation that tells us how high up in the sky we need to point our antenna. That's where we should find the satellite. Two things at this point. First one, we have one more lecture where I'm going to be covering, essentially why all of that I covered so far is not that accurate, right? Because we didn't take a lot of imperfections into account. So next lecture, I'm going to be talking about all the secondary effects that cause these calculations to have some errors. We're going to address them, and we're going to talk about how we deal with them in practice. So that's one point. That's one more lecture that we have. We have one more lecture where I'm just going to be doing problems, right? There's nothing that stops you from doing problems now. Go to the end of the chapter, go through those problems there, go through examples, because this is the lecture coming up next Thursday, right? And then the following Tuesday, you're going to have your first exam. And it's going to be calculations relative to what we covered so far, based on pretty much what you have in the examples that I did in the class, examples that are in the book, and the problems that are at the very end of the chapter. So I suggest you use this time in between to try to solve some of these problems, and make sure you ask questions when you're in class. How do you, if you get stuck about these calculations? That was one thing I wanted to. And other than that, are there any questions? Go ahead.
I have a question. In the case, we know that you said in geostationary orbit the satellite is pretty much in the same position, and that's easy.
Same position relative to the things on the ground. Right?
Yes. I mean, that's easy to point the antenna and know that the satellite is there, but in the case of a low orbit satellite which zooms across the sky every 90 minutes, how long do we have access to that satellite? I mean, do we point the antenna? How do we communicate with the satellite? Every 45 minutes, every 30 minutes?
Okay, that's a very, very real problem, right? The question is, how do you link to that? If you're on the ground, you have to have some sort of tracking system, and you have to have. There are two kinds of tracking systems. There's a mechanical system where you actually physically track the antenna. You have motors, and then you try to track this satellite. Or there can be electronic tracking system where you have an array that you steer. Antenna array is essentially an antenna that consists of many antenna elements. By adjusting the phase and amplitude to these antenna elements, you can actually change its pattern, right? So by doing so, you can actually have a beam that steers through the sky without physically moving antenna, because physically moving antenna is a complicated thing because the friction and corrosion and all of these other things. So you have to have something that is really meticulously designed and also meticulously maintained over the period of life. Right? So that's one option, and you see even at this day and age, this is a complicated task, and those antennas are typically very expensive, and there's always question of their reliability. To give you an idea how expensive they can be like a $500,000 or $1 million just for that antenna that tracks. But you sense right away that that's a very real problem, because we have LEO satellites, and we have now, if you look at just International Space Station, the US one, and there's, I forgot the name of it, but there's Chinese also operate International Space Station. So there's a real need to be connected to these LEO satellites all the time. And practically how we do it today is we actually have something which are relay satellites that we have, we call them in the US TDR satellites, TDRS satellites. The tracking and data relay satellites, which is essentially satellites that are in geostationary orbit. And then you have, for example, those LEO satellites talk to these guys, and then they relay the data to ground system. Now, beauty of that solution is in the following. When you communicate from LEO satellite to a teeter satellite, you're going essentially through free space. And what that means, you don't have to go through atmosphere. And that allows you to use relatively high frequencies, communications in a Ka band, let's say, that's in a 20-30 gigahertz range, are relatively easy to achieve there because you don't have rain to deal with and you don't have all the attenuation that comes with the atmosphere. Also, the higher you go in the frequency, your ability to point also becomes better because, you know, for the same size antennas, because your wavelength is smaller, you can design antennas which are much higher gain and much narrower beam. So what we do is we usually go high frequency links from the LEO satellites to the telemetry and then the relay satellites, let's say the Ka band and then the Ku band or C band or some lower frequency band, you feed those links back to the ground, right? And that's what right now I think there's several teeter satellites and they're actually so as you fly around you kind of send the data to one and then you hand over to the next one and you hand over to the next one, and for the good part of the globe you have coverage, right? So all the LEO satellites should always find a relay satellites that they can use to communicate to the ground.
But the tracking problem just moves to teachers.
Yeah, the tracking problem moves up in space, but it's electronic tracking and to an extent, right? So, no, it's mechanical, mechanical. So you have to. It's a relatively complicated problem and links to you know, Kalman filtering and all these nice things that you learn in adaptive filter theory. Go ahead.
For phased array antennas, what's the purpose of beamforming or beam steering in reception? Because I can see, except for scanning, because I can see in transmitting you can.
Okay. Look at the task, right? Let's say you're at the International Space Station, right? And your teeter satellite is geostationary satellite, but you're zooming really fast. So what happens is your position of your antenna that you're communicating with changes all the time, right? So you need to change, you need to repoint that antenna.
But if it's teachers, then it just stays 1 point. I mean,
It stays 1 point relative to the ground. But to the LEO satellites, the position changes, right? Here's a globe, right? Here's the geostationary orbit, right? Let's say this is your teeter satellite, right? And it has a, you know, it has Earth stations here. So these two guys communicate over the fixed link. They rotate synchronously, so nothing changes there. You design this link, it stays constant, you know, all the time, right? You point antennas, and except for small corrections that you do for repositioning of the satellite, nothing changes. But think about LEO satellite. That guy, you know, I'm put it in inclined orbit. So that guy kind of zooms like this, right? So you can see that its position changes. When it's here, you know, it needs to point in this direction. When it's here, it points in the same direction, but you see that that direction changes. Furthermore, when it goes behind the Earth, it needs to find another satellite that it needs to now point to this guy, right?
So as long as it's in this quadrant, why not just have a link with the teachers, and on the other side, you know, the Earth station can't point that way anyway, so when it's on this side, just let you.
But this is exactly what you do. When you're on this side, you talk to this guy, and then you hand over to this guy, and then when you're here, you talk to this guy, right?
So the Earth station doesn't need to scan, just.
Earth station, this station. No, this one is connected to the teeter, right?
Yeah, that was.
That's the alternative. We used to, there's another approach that you can have. you can have multiple Earth stations throughout the globe, and then as you fly with your LEO satellite, then you have to hand over from one Earth station to the other. But that becomes problematic because it turns out, you know, if you are, let's say, in one country, let's say United States, that means that you need to put your Earth station in Russia, right? Because otherwise you cannot, you know, once you go, you know, behind on the other side of the globe, there's no United States territory there, right? So, you know, the space is still kind of without boundaries, right? So you can actually put your satellite here, right, and communicate. So that's the solution, and this was actually an initiative that that NASA started specifically for this purpose, because what happens is the LEO satellites and all these satellites that we envision in the near future are going to be carrying people, right? So we're going to start spending more and more time in the space around the globe, and for communication purposes, you can maybe wait a minute or wait 10 minutes or wait whatever time you need to require to reconnect. But when you start putting people, you want to have continuous connectivity, and then that's one of the solutions that we have deployed right now. Any other questions? All right, so do the problems. Let's make sure that when we get to the problem session, you have all the questions. And try these calculations, try this Excel spreadsheets, get comfortable with how they work and how you use them to do the calculations.